All right, there we go. So today, right, I wanted to continue where we left off in our notes. This was supposed to be your assignment. You were supposed to fill out these values for L8, R8, and M8. So 8 rectangles, left-hand approximation, right-hand approximation for the R, and the midpoint approximation, right? And then I showed you guys that you could just do this on Desmos, right, to have it calculated for you. I gave you guys the link, I believe, last time. Let me see here, Riemann sums, there we go. So you can go in here and you can type in whatever function you need at the very top and then tell it where you want it to start and where you want it to end. So the function that we're dealing with is an exponential function, which is 3 to the x power, right? Like so, and it looks something like that, right? This exponential function right here, and it's going from -1. So we're going to move a to here to -1, and then b is 3. So there it is right there. Right now it defaults to, well, it was set to like 17 rectangles, but I'm going to go ahead and change it down to 8, right? Like so. And then you can kind of see the rectangle's width right here if you zoom in a little bit here, right? Each of the rectangles' width is 0.5, right? 0.5 all the way across there. Still asking you to admit. There we go. That's weird. Okay, so right now it's currently set to the midpoint value, right? As you can see, the height of each of these rectangles is at the middle of each of these rectangles right here, right, to go to the function. If I wanted at the left-hand rule, I would just change this right here. Left-hand rule, change that to a 0. So then all the values are on the left side of the rectangles, right? The height of these ones will go where the function is. So at -1, that's the left value of this first rectangle, right? And if I plugged in -1, I would get 3 to the -1, which is 1/3, which is how they're getting this 0.333 value, right? -0.5, you plug this into here, it would go 1/3 again, but this time it would be to the 1/2, so you take the square root of that, right? So that's how these things are being calculated. We're just plugging in the value of x into here, and what makes LRAM, RRAM, and MRAM difficult for some students is understanding where to get those x values, right? Because these x values change. If you're doing RRAM, right? If you're doing RRAM, if you're doing the right-handed rule, right here, the height of this first rectangle, you see it? The height of this first rectangle is where the right value is for the first x mark. Now, is it always going to be -0.5? And I'm going to say no, it's not. It all depends on your, so there's too many variables here just to try to remember like where these things should go at, right? There's where is your starting point at, where is your end point at, and how many rectangles you want. So if I wanted only 4 rectangles, for example, right, the width of these rectangles are no longer going to be 0.5. The width of these rectangles, if you look at it now, is going to be equal to 1. You see it? Because that's the way you could fit 4 rectangles on this interval from -1 to 3. If I wanted 4 rectangles, they'd each have a width of just 1, right? If I wanted 8 rectangles, that's double the number of rectangles, half the size. That's why it came out to be 0.5. And we found out that you can use this simple equation right here to calculate the width of each of these rectangles. Sorry, my dog wants to head out. Hold on one second. You don't mind, dog. You want to stay in here? You want to go outside? She just wants the door open. Can't have it both ways. There we go. All right. Sorry about that. So when you're doing this LRAM, RRAM, and MRAM stuff, right, this delta x, right, is just the width, how far apart each of these x values are, right? And if you want to think of it, it's just the width of each of those rectangles, right? So to calculate each of these to calculate the delta x's, the easiest way is to just figure out the difference between your endpoints, right? So b minus a, right? How wide is your endpoint? How wide is your endpoints from each other? What's the width of the endpoints? What's the distance? That's a better way of saying it. What's the distance between the two endpoints divided by the number of rectangles you want, right? And this right here will always give you the exact value of each of your delta x's, what they should be, right? We talked about this last time, hopefully. Now, we went and saw that if you're calculating and you're adding all of these rectangles together, right, it gives you an estimate of the area underneath the curve. And then we talked about, of course, that's not really the calculus part of it, right? You guys pointed out last time, we need to take limits of things to make this a calculus problem. And we saw it as well, right? When we looked at the limit, as the number of rectangles got infinitely larger, the delta x's, the widths of each of these rectangles got infinitely smaller. It started approaching 0. And the limit as that approaches 0 turned this problem into something that approaches the area underneath the curve, right? It no longer becomes an estimate. It actually, if I get this here to go all the way to infinity, right? These things get so close that it ends up giving you the exact area underneath that curve, right? That's what makes this calculus, is the limit as your rectangles get infinitely smaller, right? The widths of your rectangles, not the heights. The widths of your rectangles get closer and closer to 0. They approach 0. The summation of those areas gives you the total area underneath the curve from A to B. And we use this symbol right here. Whoa. We use this symbol right here called the integrand, right? The integral, not the integrand. The integrand is the thing inside. The integral, right? The integral is the function that calculates area underneath the curve. That's what it was. And that comes from the idea of adding up all these little rectangles together so that there's infinitely many rectangles there. And once we add them all up, we get the total area underneath there. And we plotted this into our calculators, and we saw like, hey, we can get this exact value of this area underneath the curve just by plugging this into your calculator, right? So let's start today by continuing this trend, right? Let's go ahead and calculate this area right here for number 4 using our TI calculator. So I'm going to go ahead and ask you guys to open up your TI calculator on your Chromebook. If you don't have it, just watch for now. You should get it. It's free for you guys this year if you have your Chromebooks. As long as you're logged in with your school account, you should be able to open it. Stop by my office hours if you still haven't done so we can get this for you. I talked to, but yeah, by the way, I should say, I talked to the assistant principal at Lawndale. When you guys go in to take the test, if you don't have a TI 84 calculator, there is, I believe there is enough for you guys to check one out the day of. So you can check out a calculator and use it during the exam, and you just return it at the end of the day. So there should be enough, I believe. Some of you guys have your own already, so you can bring that on the day of, but you can't use your Chromebooks on the day of the exam. All right, anyways, so here we go. Let's go in here. How are we going to do this here? The steps that we need to follow to calculate a definite integral is just by going to math, right? Turn your calculator, go to math, and we're going to scroll down all the way to here on option number 9, which is FN int. It's okay. Why are you whining so much, dog? You're whining too much. Relax. It's okay. So FN int right here. We'll go ahead and press enter. And you see on my calculator, on the 84, they have it so you actually can see this. So you can just plug in these values here. So this one's going from 0 to -2, right? 0 to -2. Negative sign, I have to use the little negative sign on the bottom here. Don't put the minus sign or you get an error. 0 to -2. And we have here x squared, right? With a Kaya. Sorry, my dog is being dramatic right now. With respect to x, right? You have to tell it that it's a dx because the dx is in this notation, right? It's the replacement for your delta x, meaning the difference from one x value to the next when you do those rectangles. But the the delta part of it, the d part of it, makes it so you're looking at it for very, very, very small values. That's all that notation does. Once you do this, when we go ahead and press enter, we get a negative value here. This is equal to -2.6 repeating, right? -2.6 repeating. Now, if I go ahead and sketch what this guy looks like, I'm going to make this one a little bit smaller because this is kind of in the way here. There we go. Let's make you a little bit smaller so you're not there. Perfect. All right, let's go over here now, and let's draw you out here. So this right here, again, the function that we're dealing with, right, is x squared. So x squared looks something like this. Right? That's what x squared looks like, right? But this time, the area that I'm calculating this from is from 0 to -2, right? It's going this way, right? And that area is going to be this guy right here, this area right here, from 0 to -2. That's this right here, this little chunk like so. Right? And that's what we got there. We got here -2.6. Can you guys go ahead and try this one right here? Number 5 is the same function. It looks like the same endpoints, but we have them switched around. It's going to go from -2 to 0, right? So again, how do I get there, right? How do I get there? Let's go ahead and write out the steps for doing this here. If you're on the TI-84, right, what you want to do is press math. Is it capital M-A-T-H? Yeah, it's capital everything. You're going to press the math button, right? And then go to option 9, which says fn int, right? That's how we go ahead and do these steps here to calculate this on here. So to get over here, we're going to go ahead and press math, go to option number 9. Let's actually show it, knock me. So math, scroll down. You can just press the number 9 and it'll go there and do it, but sometimes, you might not remember that. But option number 9, that's the integral right there. We're going to go ahead and do this time from -2 to 0 of x squared for this guy. So again, once you plug in the function, we just go ahead and hit x, we square that, and then of course this is with respect to x, right? We got the dx right there. So this comes out to positive 2.6. Positive 2.6, repeating, right? Now, if I were to shade this in, this is again, x squared looks like that, but it's going from -2 to 0 right here. It looks like it's the same area, isn't it? It looks like it's the same area, right? From -2 to 0 right there. I believe that is the same. I believe that is the same. So my question for this is, why is the answer in problem number 4 negative? But yet, visually speaking, it looks exactly the same. It's the same area, isn't it? The same blocks of rectangles that I have underneath this curve. But yet the value of this thing comes out negative. Why is that? The limit is negative? That's I like where you're going with that. That's kind of a good idea. But the limit is still approaching infinity, right? It's still approaching positive infinity because the number of rectangles is still a positive number of rectangles. But I like where you're kind of going with that. You're looking at the idea of the direction, Monica, right? That's hopefully what you're looking at here. If you look at number 3, right? Yeah, if you look at number 3, your integral is going from 0 to 2, right? It's going from left to right. Right? If you look at number 5, it's going from -2 to 0. Yeah, it's going from left to right. And that's how your integrals, you want to do those integral values. You can do it this way. It's not wrong. This is definitely not a wrong idea. That is a value. It's just letting you know that the direction of your area is going in that sense. I know that sounds kind of weird, direction of your area. And that's pretty much it. You just have to get the idea of that down. So they equal to each other. It's just that one's positive and one's negative, right? But the area is pretty much the same. You just have to understand that direction is what's being caused for that one right there. Okay? All right. So yeah, integrals. Really neat way of calculating areas, right? It's a very, very cool tool. It calculates the area completely without you having to just only know basic geometric shapes. You don't need to just do rectangles or triangles anymore. You can just use an integral, right? And it'll calculate the exact area underneath the curve. You just have to kind of understand what those numbers represent if it does come out negative sometimes. Okay, so it's just that part right there. So let's go ahead and keep going. Let's practice this here. We're going to go down here to the next one. Draw a sketch for each problem. Use your calculator to find the answer. Make sure your calculator is set to radian mode. If you are taking physics right now and you deal with your scientific calculator, your physics teacher asks you to have your calculator in degrees, all right? In calculus, I ask that you set your calculator to radians. So it is very important that you know which mode your calculator is in. And I say mode because that's the easiest way to check. If you press right here on the mode button, it shows you the different settings of your calculator. Later on, when you get further along the way, you will mess with a lot of these other things. Real, full, all these other guys down here. But for today, we're only going to be focusing on radians and degrees, right? So again, if you're taking physics, don't forget to change your calculator to degrees. If you're dealing with if you're dealing with calculus, don't forget to change your calculator to radians. It will mess up your answers, right? Because remember, radians, right, is 0 to 2 pi. Degrees is 0 to 360. They might seem similar, but the calculator does them a little bit differently, right? Your calculator calculates trig functions when you do integrals and derivatives in radians. It just does approximations in radians. So it's important to have your calculator set to radian. Anyways, let's see here. Let's draw a sketch for this problem right here and use your calculator to find the answer. So let's go ahead and sketch this guy right here. So this is a sine function, right? Do you guys know what a sine function looks like if we were to sketch this out? Right? Sine function, I'm going to draw it like this here. Oh, geez. I'm going to draw it like this. Let's go here, and then let's go something like all the way across like that, right? So sine starts at 0, right? Works its way up, comes back down, and then works its way up to 0 at 2 pi, right? Pi is in the middle. This right here will be pi over 2. This right here will be pi over 3. Nope, lies. 3 pi over 3. 3 pi over 2. I'm sorry, guys. I need a little wake up. Okay, so that's my sketch of the function. What does the area part look like? What part would be shaded from where to where? Where should I do my blue shading here? We look at the values on our integral. It needs to be shaded from 0 to pi over 2, right? So here's 0 right here, and I need to shade it all the way to pi over 2. So it goes up to here. So when I calculate this integral, right, and I get a number out of it, that number that comes out is supposed to represent this blue area right here. That's all that is. We just do this by plugging this into our calculator. Okay, so I'm going to go ahead and plug this in. I'm going to go ahead again. Where do I press here to do this on my calculator? For my definite integrals, I just press math, right? I go down to option 9, right? And then I just plug in those values here. So it's going to go from 0 to enter the fraction, you just enter it like you normally would. Pi would be second, and that little caret right there, you see the pi button is right there on the right-hand side. It's in blue. You have to make sure you hit second to get to that blue button. Divided by 2. That's how you press that in there. So that fraction goes up in the top. In the bottom here, I'm going to go ahead and put in my trig function sine of x. And this is a dx right there. Go ahead and press enter. And I get 1. That's it. The area that is in blue right there is going to equal to 1. All right, I'm going to give you guys, I want you guys to practice this. So I want to give you guys 2 minutes. Can you guys practice plugging this into a calculator and getting me these areas for numbers 7 through 11 for me? Is there 11 problems, or is there more than 11? I think there's 7 to 11, right? Yeah, 7 to 11. Can you guys practice this? If you don't have a TI calculator, you don't have to, Monica, but I'm going to draw them out while you guys are doing that. But you don't have to draw it. It's for your own notes, but it's kind of nice if you get the time to draw them out just to see them. But you don't have to. You can just screenshot my screen if you want to do that, because I'm going to draw them out. And when I say I'm going to draw them out, I'm going to cheat. I'm just going to copy and paste it, because we live in a world with technology, and I'm just going to use my technology. Yeah. As I was saying, though, while you guys are doing this, I'm going to give you guys 2 minutes to do this. If you don't have a TI calculator to do this, for now, you can practice using Desmos. Actually, I don't know if Desmos does it. Desmos, do you calculate integrals? Do you have the integral function here? Let's go to functions. Let's take a look and see. They got trig functions. They got stats functions. They got distance function, distributions. And they got miscellaneous. Ah, there you go. They have integral right there. Do you do this integral? Let's see if they do this integral. 0 to pi. By the way, to get pi on Desmos, you just type out pi, and it'll do it for you. Pi divided by 2, and the function that we're looking at. Use the right arrows, by the way, to move the cursor around. Get out of here. Of sine of x. Now you'll notice it doesn't do the calculation. You have to put in the dx there to let it know that, oh, this is a differential equation. Boom. And it calculates it for you. So if you don't have your TI calculator, you can use this for a temporary fix for right now. I'm just letting you know, don't get too familiar with your Desmos calculator. It's nice and all. It'll help you out for your test with me. But for the AP exam, you're not going to have this Desmos calculator. You want to get yourself used to and set yourself up for success. So please get yourself the TI emulator for your Chromebook. You don't have to, Calvin. You don't need to buy a TI-84. If you have a Chromebook from school, which you should, right? Install the TI app. onto your Chromebook so you can practice this. And if not, Calvin, if you have a Android phone, I can get you the ROMs for the TI calculator on your phone. And lastly, if this is all not possible for you, meaning that you're probably on a Windows computer. Yeah, I need that for a while, even when it ain't working right. Okay, so it's not working for you on there either. I can get you the ROM for it. Do you have a Windows computer, Calvin? If you're not using the school Chromebook, you have a Windows computer, I can get you this program. It's the same web one, but I can get you the files, and then you can just install it on your Windows computer if you trust me enough. Yeah, we can do that during office hours. Now, I'm just curious. Did the school never give you a Chromebook? Like, you don't have to use the Chromebook. You use your Windows computer, but you can't have the Chromebook on the side just for the calculator app? Is that not a possible thing? Calculate 84 on the iPhone works. Okay. Yeah, that's actually a good option if you have the iPhone. You don't need it to be perfect. I have one. It's just slow as heck. Yeah. Understandable. So that's the thing. Maybe use your Windows for this, and then use your Chromebook that's slow just for the calculator part, just to practice it. If you don't want to, either way, we just need to get you practicing on the 84 so you can get these values here. Okay. All right. So you guys should have hopefully been plugging in 7 through 11 real quick. I'm going to be pasting these guys onto here. Whoa. No, I want you here. Can I paste here? Yes, I can. They're going to be number 7. They're going to be number 8. They're going to be number 9. This is what I mean by you don't have to draw them all yourself. I'm just a cheater. I'm copying and pasting these guys. Number 10 and number 11. There we go. Of course, these do not all have the same shaded regions, so I should have copied it without that right there. Easy enough, knock me, easy enough. Look at that, just go in there and boop, boop. There we go. Haha. So for number 7, you're calculating the area from pi. And now that I've done that, my OneNote is lagging. All right, let's try this again. Hold on a second here. There we go. Okay, so let's try this again. So for number 7, I'm calculating the area from pi to 2 pi, right? That's this area right here from pi to 2 pi. Hopefully you guys do a better job with shading than I do. I don't color very well. You know how you're supposed to learn how to color between the or stay within the lines? I can never stay within the lines. Get too impatient. That's pretty good. All right. What'd you guys get? What'd you guys get for number 7 when you plug this into your calculator? What was the area from pi to 2 pi? Monica's saying is -2. We're going to write that down, right? -2. Emily, Brian as well, -2. Good job. Good job. Fatima, same as you. Awesome job. We got -2 there. All right. What'd you guys get for number 8? What'd you guys get for number 8? What's the area from 0 to 2 pi? People typing it out. Good. Good job, guys. Everyone's saying that it's 0. Right? Leslie, thank you. Thank you for joining in on that. I appreciate it. It is 0. That is correct. But isn't that kind of strange? The area from 0 to 2 pi is this area right here, isn't it? It's from here, which we found out in number 6 was a positive area. Well, part of it, we found half of it was 1, and the rest of it gives us 2. And this one right here that we just solved was -2, wasn't it? Interesting, interesting. All right. All right, number 9. What's the area from pi to 0? What's the area from pi to 0? -2. That's right, Emily. Thank you. Thank you. From pi to 0, we're starting here and we're working our way backwards, aren't we? We're working our way backwards on this one. It goes from pi to -2. I'm sorry, pi to 0, which gives us a value of -2. It's still above the curve, but it's a negative area, isn't it? And if we do from 2 pi to pi, that's this area, isn't it? What do you guys get for that one? What do you guys get from 2 pi to pi? What do you get from 2 pi to pi? 2. Just a positive 2. Interesting, huh? Oh, I should have read this one before I copy and pasted number 11 here. This is going to go from 0 to pi, isn't it? So it's going to go this way. The trig function works out like this, doesn't it? To negative pi, from 0 to negative pi. And that's going to be back here, this area over here, which is just what, guys? Did you guys get that last one? Fatima's saying 2. Emily's saying 2. Monica's saying 2. That's right. This last one right here is 2 as well. So here's what I want you guys to tell me at the end here. This is one question I want you to type out. Don't type it out. Put it into your own notes. What do you guys think? Why are some of the answers negative and some 0? Give a geometric explanation if you can. This is something I want you to write in your own notes, and you're going to submit this for me. I'm going to read this later, but that's what I want you guys to do as part of your homework, right? Look at these problems here that we calculated. We know that the calculator can evaluate these areas just perfectly fine. But geometrically, why are some of them coming out negative, and why are some of the answers coming out 0? Right? So I'm going to leave that for you guys to explain, and I want to take a look at that. Use a symbolic notation to write the integral from a to b of f of x dx. The symbolic notation was what we had earlier. It's this guy right here. This is right here. This is equal to the limit as your delta x's, each and every single one of these delta x's approaches 0, right? The widths of your rectangles approaches 0. How many rectangles do you have? Well, I'm going to have the first rectangle all the way up to the infinite rectangle of my function evaluated at those particular whatever those delta x's are, times the delta x itself for each of these rectangles. I know this still looks crazy when you look at this symbol, this whole idea of what this integral represents, right? But in layman's terms, if you want to think about it, and it also comes back to this answer right here as to why some of them comes out to be negative and some come out to be 0, it's technically, what you're looking for is technically just the area, right, above the x-axis minus the area below the x-axis. That's pretty much it, right? When you're calculating this integral, you're just calculating area, right? And it's between the curve and the x-axis. And you notice if the curve is below the x-axis, the area that comes out negative. And that's just telling you like, hey, the area is representing down here. If you do the area from right to left and it's above the x-axis, it's also going to come out negative. And that's just because it's having you calculate, it's just the direction of where your area is going. So if you're calculating for the area underneath the curve, you really want to go from smaller value to greater value. You don't want to go the other way around. You want to go from left to right. But it still works. You still get the same value. Just understand that if you do it the other way, it comes out negative. Right? That's that right there. So okay. So hopefully you guys can see that you can calculate area very easily now, right? You don't need to do these LRAM and RRAMs to approximate them, but you can, right? You can. But now we found out that if you know what the function is, right? If you know how to represent the function of that curve, and you know where you want to have your endpoints on there, you know that you now have a tool to calculate the area underneath that curve. And again, if your TI calculator isn't working, you can't figure that out, go to Desmos. Desmos is a free app. You can go ahead and use Desmos to do your integrals for now, for homework and whatnot. Okay? All right. Let's go over here. We're going to go off to this next section right here. We're going to verify this thing called the Fundamental Theorem. It's technically the Fundamental Theorem of Calculus. Can you go to the definition, please? Of course. Was it this one up here? Wait, which definition? Oh, up here? There we go. Okay. Sorry. Give you a chance to write that down. Let me get some water while you do that. All right. Hopefully you got that down. We're going to go to this next part over here. The fundamental theorem. Whenever you hear something called the fundamental theorem, it's usually important. Usually. Conjecture. What is the relationship between the area function and the original function? So, you guys agree, right? This is actually a function that calculates area. You have to plug in values for your endpoints, your a and your b. When you plug in your values for your a and your b, the output you get is the area between those 2 points of this given function, right? So I'm going to name that right there. I'm going to name that a of x. We're going to call that the function that calculates the area of a given function that's there, right? So a of x is a function that calculates the area between 2 points of any function. And we're going to say this function today, for this function, we're going to say that f of t is going to be equal to 5, right? So can you picture that right there? F of t equaling to 5 is just a horizontal line that goes across, right? It's just a horizontal line that goes across. Don't write this down. I just wanted to show you what this is saying right here. So f of t, here's a graph of f of t. It goes up to 5 and it just goes straight across like that, right? Now, what a of t does, a of t is going to calculate the area from 0 to whatever x is, right? So a of x, right, is going to be equal to this guy right here, from 0 to x of 5 dt. Now, what I'm saying is this. If I calculate the area up to where x is equal to 1, I want to know what this is equal to. A of 1 would be equal to this guy right here, right? That's what a of 1 would equal to. If I go to 2, right, a of 2 would be equal to all of this area right here, including a of 1. So a of whatever number you're calculating is going to give you the area underneath that curve where f of t is equal to 5, which is, again, it's not a curve, it's just a straight line. And you'll be able to calculate this area just using rectangles, right? But we're going to be practicing with our integrals for this one. Okay, so here we go. So if you guys could, right? So for a quick example right here, right? A of x, when x is equal to 0, what is that going to equal to? Well, when x is equal to 0, right, a of 0 is going to equal to the integral from 0 to 0 of 5 dt. Well, what does that look like? Well, remember, this is just a straight line that goes straight across at 5, right, for f of t, right? The area function is asking me to calculate the area from 0 to 0. What's the area from 0 to 0? What's this area right here? You guys know? It has a height of 5, but it has a width of 0. So what do you think that area is going to come out to be? All right, what do you think that area is going to come out to be? If it has a height of 5, but the width of that rectangle is 0, it gives you an area of 0. That's right. That's right. We're going to plug that in right here. Right? But of course, we don't need to do this by hand. We could just plug this into our calculator, can't we? So I can go ahead and do that real quick. Let's just do that real quick here, just to practice it. Right? We're going to get math. We're going to go down to option 9 and plug in those values. 0 to 0 of 5 dt. Now, it says dx here, but that's just because I can't actually plug in a dt in there. Okay? We're going to plug it in like that. Go ahead and press enter. And it's 0. Right, so let's fill these all out. I'm going to go ahead and press second, press entry, and it actually retypes in what you typed in earlier, so you don't have to keep retyping the whole thing. And I'm going to plug in all these values here, 1, 2, 3, and -1. So let's go ahead and calculate these ones right here. I'm going to change these values. It goes from 0 to 1. Right, let's see what that one gives me. That gives me a 5. Right, let's go again. Second entry, and then put the same thing, but now instead of going from 0 to 1, let's go from 0 to 2. Right, 0 to 2, that gives me 10. That kind of makes sense, doesn't it? Because it has a height of 5 up here, and if it has a base of 2, this area right here would be 10, wouldn't it? Let's go to 3 for the next one. Right? 0 to 3 for this guy of 5 dx, or dt it's supposed to be, but you know, we're using the placeholder there. That's going to give me 15, right? And let's do this last one right here. From 0, whoops, let's go ahead and press second enter. and get this last one right here, from 0 to -1 of 5. That gives me an area of -5 from 0 to -1, from 0 to -1. There we go. So I have a bunch of data points right here, right? I have a bunch of data points here. 0, 1, 2, 3, and -1, and then I have the output values of 0, 5, 10, 15, and -5. Let's see if we can find a function that lines up with these points right here, right? Let's see if we can find a function that lines up with these points right here. Sorry. So check this out. If I were to plot these points, right, use the stat plot feature, I'm going to show you real quick right here. I'm going to put these in the x values right here into L1 and the corresponding a of x values into L2. You don't need to do this, but if you want to, you can. I go to stats and I go to edit, right? This is where we were practicing calculating all the areas there. I'm going to go ahead and continue here and practice by just graphing these points now. So I'm going to plug in these values here. 0, 1, 2, 3, and -1, right? Those are my 5 values I have plugged in here. And the corresponding area values that we got out of this was 0, 5, 10, 15, and -5, right? The stat plot feature, you can actually graph these points onto a scatter plot, right? Or dot plot. Is it a dot plot? No, it's not a dot plot. It's a scatter plot. So I'm going to go ahead and hit second and go up here to stat plot. And I'm going to turn on plot 1. So I'm going to go ahead and press that. I'm going to turn you on. It is a dot plot type. The x values is in L1. The y values is in L2. I'm going to make these big dots right here. I'm going to go ahead and go to graph and take a look at that right there. So can you guys see it okay? The dots that show up right there? This is -1, -5. This is 0, 0. This is 1, 5, 2, 10. 3, 15 seems to be off my chart. So I can adjust my windows, right? You can always mess with the windows if you know your input and your output values. I'm going to go ahead and press Windows right here. I don't need to go all the way down to -10. I could probably just go to like -3, right? As far as I need to go. Right? How do I know to go to -3? You can go to like -1 because if I look at my x values, right, the smallest value is -1. I'm just going to go to -3 and I'm going to have my largest value go up to 5. I'm just picking these points arbitrarily just so that they fit. The y values, I don't need to go down to -10, but I could, right? Because the smallest value is -5. But the largest value I have is not 10. The largest value I have is 15. So I might just have it go to 20, right? I might go from -10 to 20. And when you reset these values here, your windows get warped a little bit, but you can see the dots a little bit clearer, right? You can see the dots a little bit clearer. Now, my job is to figure out a function that would hit all of those dots, right? That hits all of those dots. So at 0, 0, 1, 5, 2, 10, 3, and 15, -1 and -5. Does anyone know of a function that fits all of these data points here? Does anyone know of a function that would hit all those data points we have graphed right there? 3x, 2x, let's try it. Let's try 3x first. 3x, let's go ahead and graph the 3x function. Oh, so close, so close. Very close, but it doesn't hit all of them. Let's try 2x. Let's try 2x. Boom. We graph it. It seems to be going the other way. 5x, my bad. Oh, okay, 5x. Let's try that. 5x. 5x looks like it's the function that hits it. So if our area function is defined to be the integral from 0 to x of 5 dt, but we also see that this area function can equal to 5x. Can't it? Can't it? Interesting stuff. No? Interesting stuff. Now, check this out. Let's make a sketch of the function y is equal to f of t, right? So I already did that. That's this guy right here. Let's erase all of that. Y is equal to f of t, right? So there's my sketch. Okay? Shade the region on the given interval, use a geometric formula to find the area of the shaded region for a of x. So let's go ahead and take a look at this one. Let's make this a little bit bigger here. Let's make that a little bit bigger here. Let's come down here. All right, let's bring you like so. There we go. All right. So here's the thing. If x was equal to 1, right? If x was equal to 1, the area was just going to equal to 5, right? If x was equal to 2, then the area was equal to 10, right? It was literally, if you realize this, you can say that if this was just equal to x, what's area equal to a of x? It's just equal to 5 times however far you go on your x value, isn't it? So it's going to equal to 5x, which is exactly what Brian says was the function that fits those lines for those dots, right? The geometric formula for this guy to find the area of the shaded region, a of x, is going to equal to 5x. Huh. If we use the definite integral formula to evaluate this, right? Check this out. Let's just say a of x right here is equal to the integral from 0 to x of 5 dx. Right? It's just equal to the, if you take a look at the shape right here, right? Let's say I drew this again here. Let's say it was going from like 0 to 2, right? 0 to 2 of 5 right here. So here's 1, here's 2. Right? If I were to calculate this area, right, I kind of have to calculate where the x goes. In this case, if it goes up to 2, that's this guy right here, and subtract it from where it starts. Okay? So what this is equal to, right, it's equal to 5 times, because 5 is just the height of this function, times the how far it goes out right here, which is going to be 2 minus 0 in this particular example, or if I'm just using x as my example, it would be x minus 0. I know this sounds weird, but this right here is just going to be equal to 5 times x minus 5 times 0, which of course is just what? It's just 5x, isn't it? I know some of you guys are probably like, what the heck is he going on about here? But that's the idea here. The definite integral, right, is just this thing that helps you calculate the area underneath the curve. And if we're looking at this basic area right here with this line, I can show you that this integral of this function just comes out to be this. It comes out to be this 5x. Here's where I'm trying to go with this. Okay? The integral from 1 to x of 5 dt. And let's say we didn't start at 0. Let's say we started at 1 instead. Let's say we started at 1 instead, right? That's going to be equal to 5, which is the height of your function, right? Which is the height of your function, okay? Times x minus 1, right? Wherever your x ends up at, and then your starting point was at 1. So if I had the same function right here, which is 5, like this, 1 is right here, right? To get the area, I need to go to where x is. The height of my rectangle is still 5. That's where this 5 comes into play. The base of my rectangle is the difference between where x is from where you started, x minus 1, right there, okay? Which, of course, is just going to come out to equal to 5 times x minus 5 times 1, right? Or in other words, just 5x minus 5. Whew. Now, this one changes up a little bit. If we go to -1, I'm kind of shortcutting through this. You're supposed to do this whole thing up here that we went from a to e for these values down here. But I feel kind of bad about rushing through it, but we don't really have the time. Maybe I should just let you guys do this one. Yeah, maybe I should just pause here and let you guys try this one out for yourself. Yeah, you know what? I'm going to not ask you to do number 3, but for you guys to finish up this worksheet, I want you guys to try number 4. You don't have to do this right now, but I want you to make a table. Go from 0, 1, 2, 3, and -1 for this function this time. F of t is equal to t instead of f of t is equal to 5. Right? So we did this for f of t equals to 5, and we said a is equal to this. Right? So for this one right here, when you start this one off, right, let a of x, for number 4, let a of x be equal to the integral from 1 to x of t dt. So do the same thing. Make a table for this one, but instead of it being 5, you're going to be a value of whatever t is at that point. So plug in these values here. So this is going to be x. This is going to be a of x, right? So just for a quick example here, right? Let's go for 0 right there. All right, and you're going to plug in this value for me right here into your calculator. So the way you plug this in, by the way, I know it's a t value, but we're just using it as a placeholder. So I press math, go to option 9, right? This is going to go from 0 to 0 of x dx, which is just going to come out to 0. That one's not a good one. Let's go to 1. Plug in that same value right there, but it's going to go from 0. Oh, wait, hold up. Is this supposed to go from 0 to 1, or is it? Oh, it's supposed to start at 1. My fault. My integral there is wrong. Sorry. That should be from 1 to 0. 1 to 0. There we go. We get here negative 0.5, right? From 1 to 1, that would be 0, and then do it for 2, and so on and so forth. Okay, so get that value in there. Math 9. Let's go from 1 to 2 of x dx, and we have here 1.5. 1.5. No, we don't have time for this. Okay, so we're just gonna have to go through here. I'm just gonna have to give you these things. I feel bad. All right, let's just. Sorry, this worked better last year when we had more time, but I keep looking over and we don't have enough time to go through and hit all of this. So I think I might have to just cut my losses here and just get you guys into the get you guys into the fundamental theorem of calculus. I think that's what we're gonna have to do here. But this is the part that you're supposed to lead to, and I feel bad. Here's what it's supposed to lead to. When you do all this stuff and you calculate all these things, you actually find out that this function right here, when you do this integral, it comes out to look like this. You ready for this? It comes out looking like this. It comes out to 1/2 x squared minus 1/2 times 1. And this x squared right here kind of is related to this part. But the thing I kind of wanted to show you is this. And I feel, again, I'm sorry if this doesn't make much sense. I promise you, like, I kind of messed up this lesson for you. But here's the deal, right? If you just look at this function right here, right? This a of x, this is technically what a of x is, right? And a of x is equal to the integral of this, right? So what I'm saying is this. A of x, right, is equal to, for number 4, right? It's equal to 1/2 x squared minus 1/2 times 1, which of course is just equal to the integral from 1 to x of this function right here, f of t dt, right? But check this out. If I take the derivative with respect to x of a of x, right? If I take the derivative of this guy right here, the derivative of 1/2 x squared, well, the derivative of x squared is just 2x. 2x times 1/2 is just going to come out to be equal to x. The derivative of 1/2 times 1, that's just a constant. That's just going to come out to be equal to 0, right? That's going to be equal to the derivative with respect to x of the integral of from 1 to x of f of t dt. And what's kind of interesting about this is that if I take the derivative of something I take the integral of, I just end up with the original function evaluated at x. I know this sounds weird, but hear me out. If I go back to number 1, right? And the area of x for that one was equal to 5 times x minus 5 times 1, right? That's what this guy was up here. But again, this is equal to the integral from 1 to x of f of t, right, dt. But f of t dt for number 2, I'm sorry, not number 1, number 2, right here. The f of t dt was just equal to 5. But check this out. If I take the derivative of this with respect to x of this area function, right, this guy right here, the area of the derivative of 5x is just going to equal to 5. The derivative of 5 is just going to equal to 0. So the derivative of this area function is just equal to 5. Just what we started off with. The derivative of the area function over here was equal to x, which is what we started with, kind of. It was t, but it was t evaluated at x, isn't it? And again, this is all equal to the derivative with respect to x of the integral from 1 to x of f of t dt. And what I'm saying is this, basically. F of t, in this particular case, was equal to 5. When I take the derivative of the integral, it kind of ends up the same thing. And that's kind of like what's happening here. If I take the derivative of the integral, this function, f of t, is technically just equal to t by itself. It's just a variable by itself with nothing else. And that's what's happening over here. It's just x by itself because that's where we're evaluating it at. The fundamental theorem of calculus is this, and I kind of went a roundabout way of kind of showing this, but if you take the integral of a function, calculates the area underneath that curve. If you take the derivative of that function, of that integral function, you end up back where you started. And that's kind of a big deal in math. If you do an operation to something and you end up somewhere, and you do another operation that takes you back to where you started, we usually call that the inverse function. If you had x plus 3 as a function, x minus 3 was its inverse function. It would take you back to where you started, right? If you have 3 multiplying x, right, the inverse of that would be x divided by 3, right? And that, I don't know if you see this pattern. When you're in elementary school, you learn addition, right? Right after you learn addition, you learn subtraction because it's the inverse. It takes you back to where you started. If you learn multiplication, the next thing you learn after multiplication is division, right? Because division is the inverse function that takes you back to that. And David's kind of catching on to here. The inverse of a derivative function is the integral function. And I find that strange, but it works out. If I take the integral of a function and then I take the derivative of that result, I end up back where I started, which means that the inverse of a derivative is the integral, and the inverse of an integral is a derivative. I'm going to skip over here. This is actually part of your homework. You can do this later here, but it builds off of this part right here, which I'm going to write out for your notes right now. So if you guys could copy this down. The title of this right here, what I've just explained to you, right, is called the Fundamental Theorem of Calculus. Part 1. I'm not making this up, by the way. There's 2 parts to this fundamental theorem of calculus. This is the fundamental theorem of calculus. The fundamental theorem of calculus states this. If I take the derivative with respect to x of an integral starting at any value, it doesn't matter if it starts at 0, if it starts at 1, any constant a, and I take it to any value of x of a function, and any function I'm talking about here, dt, it's going to equal to that function evaluated at x. Because when you take the integral, we find out this particular function that it's equal to, but then you take the derivative of that function and you just end up back at where you started, but evaluated at whatever this is. I know that sounds weird. It sounded weird to me the first time I saw this, but let me show you an example of this. How does this mean? What does this mean? So if I was asked to find the derivative with respect to x of the integral from 3 to x of 2 dt, you ready for this? this would just equal to 2 because the derivative and the integral function, I don't want to say it this way, but they cancel. They don't actually cancel, but it takes you back to where you started. And if you don't believe me, right, the function 2 is a horizontal line that goes across that 2, right? And if you do the integral of this, right, you're calculating the area of that, right? So the area is this, the height of your rectangle times the base of your rectangle, right? And the base of your rectangle would be x minus 3, wherever it goes to, right? Which in other words means that this function right here, this integral function, right, would give me this output right here. It would give me 2x minus 3. I'm sorry, 2x minus 6. This right here is the function that would calculate the area from 3 to x, whatever my x may be. If my x was at 5, right, then the area underneath the curve would be 10 minus 6, which would just be 4, which kind of makes sense, right? Again, if you graph that out, right, it goes along here. Here is 3, here is 5. The area that should be here is supposed to be 2 times 5 minus 2 times 3, right? Which makes sense because 2 times 5 is this entire area right here minus this area right here. So it comes out to be this area, this chunk right here. So that's that part right there. So this right here, this represents that integral. If I take the derivative of this integral, this is what I'm saying. This is what the part that comes out weird. If I take the derivative of this with respect to x, the derivative of 2x, why, that's just 2. The derivative of negative 6, that's just 0. So the derivative of this integral kind of just takes you back to where you are. And it doesn't just work for this one. It works for any function you can write out. Check this out. If I have here, let's say I was asked to find, right, another function. Let's say it was dx of the integral from 10.5 to x of 3t squared dt, right? This is just going to equal to, I'm letting you know right now, the derivative with the integral, you're going to end up back at your original function, 3 something squared. But that something is not going to be, oh no, this is no longer in your Cami notes. This is no longer in your Cami notes. So actually, thanks Monica for pointing that out. This is actually off of your Cami notes now. So yeah, this is not going to go part of your Cami notes. Sorry, I should have said that. But here's the thing. What's that something that's in there, right? It's 3 of some stuff squared because that's what the original function was. It's 3 of some stuff squared. But you've gone now when you integrated this, you evaluated it at this new variable x. And what you end up with is not 3t squared anymore. You end up with 3x squared. 3x squared. When you take the integral of something and then you take the derivative of it, you kind of end up back at where you started. That's because when you take the integral of something, you're doing the inverse of a derivative. So then when you take the inverse of a derivative and take the derivative of that, you just end up back with where you started, but with a little catch. That little catch being, what did you evaluate it at? What did you evaluate it at? What that leads to is this, right? What that leads to is this part right here. If I take the derivative with respect to x of an integral of a function f of x dx, that's just going to equal to f of x. That's what this whole roundabout thing is going. I know it sounds like, why didn't you just say that to begin with? But that's a big deal, right? We didn't know that an integral and a derivative have this relationship, but it does. If you take the integral and then you take the derivative, you end up back at where you started. What does that mean in our case here? Well, here's the thing. This integral of f of x dx, we have a special name for it. We even have a special symbol for it. The integral of f of x dx, right, is going to be equal to capital F of x. And if I take the derivative of capital F of x, I end up with this guy, capital F prime of x. But of course, this is all still equal to f of x, right? So here's what we name this guy right here, this f of x, this capital F of x. You ready? If I take the integral of f of x dx by itself, we end up with this guy, capital F of x. This capital F of x, we don't call it the inverse of f of x. We don't call it the inverse of the derivative. That just sounds weird because we take derivatives of inverse functions, but that gets confusing. Oh, it's the inverse derivative. Instead of calling it the inverse derivative, we call it the antiderivative. That's what this capital F of x represents. It's the antiderivative of a function. Of, in this case, f of x. If you thought ahead about it and realize what we're going with next is this. Our whole first semester and a little bit of second semester, we've been practicing calculating derivatives of functions. The second part of calculus is calculating the antiderivatives of functions. Meaning you go backwards now. If you know what this is, you can find its derivative. Now, if I give you a derivative, you should be able to find out what the original function was. That's our ultimate goal. So let me show you an example of this. You ready? So here's an example. Evaluating integrals, right? Well, not evaluate. Let's not leave any words for it right now. Let's just say I was given a problem like this and I was asked to solve this problem. I have here the integral of 2x dx. The integral of 2x dx. What's my function that's in here? Do you guys see it? What's my f of x in this problem? F of x in this problem is what? 2x. Very good. So here's my question then. What's the antiderivative? What should my original function have been so that when I take the derivative, I end up with 2x? And David's saying it should have been x squared. X squared. So what does the integral of 2x dx actually tell us to find then? It's actually just going to be equal to x squared. And that's it. That x squared is the antiderivative of 2x. Now there's more, of course, but I'm going to pause it here. Does that make sense? What I've just written out. I know I've gone a really long way to go about this, but if you got lost along the way, just realize when you're doing these integrals, right, aside from calculating the area underneath the curve, you can actually find the original function. And all it is just finding out what the antiderivative of the function you're dealing with is. So back up here, right? Check this out. 3t squared, right? 3t squared. You ready for this? If I took the integral of 3x squared dx, what's the antiderivative of 3x squared? If f of x was equal to 3x squared, what was the antiderivative of this? Anyone have any ideas? What, if I were to take the derivative, would give me 3x squared? Monica and Leslie are both saying x cubed. That's what this should be. The antiderivative of 3x squared should be x cubed. Now here's the part that I was trying to make the connection with, and I'm so sad that I didn't get to make the beautiful connection with you guys because I messed up on the timing on this, but check this out. If I take the derivative of that, right? If I take the derivative of x cubed, right? I go over here. I go ahead and say, hey, what's the derivative of x cubed, right? Thanks to the power rule, what is the derivative of x cubed? Why, that's just 3x squared, isn't it? That's what I was saying up here. If you take the derivative of an integral, you just end up back with the function that you have. And that's what the fundamental theorem of calculus is saying. That's how those two things are connected. That's how the derivative is connected to the integral. That's how the integral is connected to the derivative. Seems simple enough, doesn't it? Now, functions get a little crazy sometimes. If you guys remember, when we were doing all these derivatives, The anti-limit, is there? No, there's no anti-limit. Limit itself is its own basics of it. But here's the thing. If you guys remember, right? We didn't just learn derivatives using power rules. We learned derivatives of different types of things, didn't we? Chain rules, yeah. We are going to have to do the antiderivatives using chain rules. Not for this chapter, not for this test, but next chapter we will. But before we get there, before you get ahead of yourself, let's just start off with something that's a little bit more complicated, but not as difficult as the chain rule. How about this one? Check this out. Let's say the integral of the function cosine of x dx is the function that we're looking at. Right? What would that look like? Well, the function that's in question right here, f of x, is equal to cosine of x. So my question is this. What's the antiderivative of that would give you cosine? Oh, darn, Monica, you already got it. And this is the part that gets tricky. Is it sine of x, or is it negative sine of x? This is where I used to mess up on. The derivative of cosine is negative sine. But that's not what I care about. I want the antiderivative of cosine. So here's my question. All right, should this be sine or should this be negative sine? Well, if it's negative sine, what's the derivative of negative sine x? Does anyone know? The derivative of negative sine x is negative cosine x. The derivative of just sine x, why, the derivative of just sine x, that's cosine x. So it's not negative in this case. The antiderivative is just sine of x. This right here, this is the antiderivative of cosine of x. That's the part that always trips everybody up. The derivative of cosine is negative sine. The antiderivative of cosine is positive sine, because the derivative of sine is cosine. Anyways, know your trig functions, right? If you know your derivatives for your trig functions, you'll know your antiderivatives for your trig functions. Okay? All right. With that being said, I think I can show you a couple properties and we can wrap it up here. As for this worksheet that I'm going to have you guys turn in, here's what I want you guys to do. So ignore part B, right? We did what we could here for part B. I was supposed to have you guys do this on your own, but just know that just leave that for B. So let's say B is done, right? Let's go on your notes here. Part B is done, okay? Part C, this one is what I want you to try to fill out. Do this example 2 right here. So this is going to be the second part of this. When you finish this, hopefully you finished the first part of this as your homework before, example 2 up here. Hopefully that's done. And then you can come down here and finish off this right here. Fill out these values. What is a of 0? What is a of 1? What is a of negative 1? What is a of negative 2? Right? And plot, this one right here, graph this one over here, and then this one over here, graph it on a graphing calculator, screenshot it, and paste it onto your notes for me. It says to sketch it, but you're doing it on your computer. You can go ahead and just plot these points using either the TI calculator or Desmos, and then just sketch the graph of that, or copy and paste those dot plots on there. You can draw on there if you want, or you can use the function to try to draw it out for you. So try to do that for your homework. Okay, so fill out these questions right here, right? Give me the sketch of it. And this is the part where it gets interesting. On your calculator, you can actually use your calculator to graph your function. Can you guys fix this for me? For number 3 right here, this should not be like this. This should actually be fn int of 2x minus 2 from 0 to x, comma x. So if you're using an older TI calculator, this is what it would look like if you typed it in. If you're using the TI-84 or higher, it should look like this. Type it in like this. It would be from 0 to x of 2x minus 2 dx. So you can actually plug this into your y value. You can actually graph this one. Okay? So check this out. This is what I mean here. We sketched this graph right here, and you guys actually told me that it looks like 5x. But check this out. If you actually plug it in like this as math 9 and you do the integral from 0 to x of 5 dx, it'll actually graph 5x for you. It just takes a little bit longer because it actually has to do the calculation. You see it? It's calculating the area at each of those points by doing the integrals all the way there. How do you get there in your calculator? To do the graphing part, you go ahead and press y equals, and this is where you get to type in your function. In this part of your homework, you're going to be typing in the function instead of 5 dx, you're going to type in 2x minus 2 instead from 0 to x, and then see what that graph looks like. You're supposed to do this after what you sketch what the graph, what you think it might look like based off of what your answers were from A to F. Okay? So we'll do that first. And then you can try plugging that in there. If you're doing this on Desmos, I believe you can just, I believe this will graph it on Desmos. Let me see here. Hold up a second. Give me 1 second here. Will it do it? Sadly, it will not. Sadly, it will not. So Desmos is actually not going to graph this for us. Integration bounds can't be dependent on the integration variable x. Yeah, so it won't do it. It won't. It'll only do it on your TI calculator. So just a heads up on that one. So it doesn't look like Desmos would do that. All right, anyways, I'm going to leave it there. There's properties that we need to talk about when we go into this fundamental theorem of calculus, but for right now, it's a lot for you guys to do those properties and do those problems. So what I want you guys to do to focus on is just finish up this thing right here and then submit it when you do finish it. Calculate these values for me for this f of t right here, 2t minus 2. Sketch that graph. Calculate these values from -2 all the way up to 3. And then answer these questions as best you can. If you can't answer some of them, let me know which ones you can't. But I want you to try all these. So that's going to be your homework. Finish off this worksheet. You should be able to submit this now. And that's going to be it for today, guys. We'll continue up with the fundamental theorem of calculus on Thursday. All right? All right, guys. Finish up this worksheet. That's it for me. And that's all I'm asking from you. Once you finish up that worksheet, you should be done with this. Go ahead and submit it onto Canvas, on Cami, and you're good to go. All right, guys, that's it for me. Have a good rest of your day. I'll see you guys on Thursday. I do have office hours today from 1 to 2 if you have any questions about the crazy stuff that we did today. I'll see you guys later, all right? Have a good one, guys. I'll see y'all on Thursday. Bye-bye, everyone. Have a good rest of your day.